Hi everyone, my name is Huang. My presentation topic, Data Parallelism in Machine Learning. Here the outline. First is the introduction to machine learning concept. Second is the breakdown of data parallelism, what it is and an analysis. Then I'm going to talk about some strategy using data parallelism. Finally is the vision for the future. So just a quick overview, machine learning recently have developed at a significant speed. It plays an important role in many economical fields such as technology, biology, education, and this happened because of two main reasons. First is the ability to collect more and more data from survey, from advertisement. Secondly, we have developed more and more strong computational machine. So right now, what is machine learning? Basically, machine learning is an algorithm that have create a good prediction model based on the given data. Let's go to some example. We want to predict the house price in Santa Clara based on the size of the house. So we have the y-axis is represent the price and the x-axis represents the size. So and now we collect the data and then we plot into the graph. What we want to do is we want to try to find a good line that match to all of our data. In other words, we want to find the parameter theta 0 and theta 1 so that we can have such that line. Before doing that, let's talk about the loss function. Loss function represents how good the prediction is. There are many versions of this function. Right now, let's assume the loss function. What we want to do is measure the difference between the predicted value and the observed value. So our goal is try to minimize this function. The less the loss function is, the better the prediction. So here's how gradient descent works. We update the parameter in terms of the gradient, the slope of the loss function. So W here is the parameter that we want to update. So the whole thing here, this is the gradient of the slope of the loss function. So alpha is the learning rate, is how far the step we will go. So I'll explain more in the next slide. So the minus sign here is make sure we're gonna go to the direction of the minimum. Right now you can imagine gradient descent. It's just like walking on the valley and you want to go to the lowest of the valley. So here's some image. So let's see. So right now j theta 0, theta 1 represent the loss function. So let's say you are here right now. Gradient descent, it's just like you go each step one at a time. Like each iteration you go one at a time. You go and then the global minimum. So alpha here is how far the step. So the bigger the alpha is, the quicker you will reach to the global minimum. Note that depend on where you are, you may reach another local minimum. So that's why we have to keep doing so until we find a good minimum. So what's the problem? One single CPU, we need multiple days to compute and return the result. Secondly, put all of terabyte of data in single machine is impractical. To avoid that problem, that's why we need our data as a model to distribute it into many computers to update the parameter in parallel. And that's also the introduction to data parallelism. Data parallelism refers to the distribution of computing data in many different machines to boost up the computational speed. Data usually split it into nodes. Nodes are used to iteratively update the gradient descent parameters. There are two types of data parallelism: asynchronous, which is many computers communicated through a shared memory; synchronous, many computers communicated through a message passing. Asynchronous gradient descent. For example, suppose we have a CPU that can run a multi-threaded program. For each parameter, we have one thread or one process to compute and update the parameters. So let's say we have a dimensional vectors of parameters x1, x2, x3, and x to the d. So we have one process responsible to compute x1, another x2, another x3. So as soon as this one finishes computing x1, it updates x1 into the shared memory, and the other threads can use the update parameters to continue computing. So what is the problem that can happen to this model? The first problem: will the gradient descent still converge under this inconsistent iteration update? Because x1 can be updated, and then x3, and then xd, and then x2. There's maybe a chance that gradient descent is not converged. However, it's proven that asynchronous still converge, but at rate which is slower than the serial version. Why? Because the order of which each thread can be executed depends greatly on the schedulers. So x1 can be updated, and then xd, and then x2, because it go in the order that only the scheduler know which one go first. So this causes a problem. Let's look at the image to understand why it caused the problem. So usually when we update x1 and then x2 and then x3, it's guaranteed to go in a certain path. Usually it goes straight down this road. But when we update x1, x2 in random orders, the path is not guaranteed. We may go this around and around, go this part and then come here. Or it can go like this and then come here. So it takes a longer time than the serial version, which is one step at a time. And that's why asynchronous can sometimes be slower than the serial version a bit. Now let's talk about asynchronous gradient descent. Asynchronous gradient descent is updating parameters simultaneously in real time. So we have many computers, and each one has its own set of parameters to update. And many of their computers, they are connected to a server. So right now imagine computer 1 is a worker 1, computer 2 is a worker 2, and so on. So because they have each own set of parameters, so usually worker 1 will update parameter 1, and worker 2 will do the same thing until the worker n update parameter n. So right now, let's introduce you to a new term, which is the mini batch. A batch is each iteration updated. So this is one iteration, and after each iteration, n parameter will be updated, and they will be sent to the server. The server will update each parameters, and then the data have also continued updating P2 another batch, and after a second batch, n parameter will be updated, and they will be sent to the server. So what's the problem? Under large-scale model, the communication and the synchronization cost between each computer will be significantly large. Why is that? Because in the large models, there are more and more thousands of data that will need a lot of transferring between each computer and the server. So like when you uploading something which is very large, it takes a long time. The second problem is the fastest node have to wait for the slowest node to finish in order to update the parameters, because it's going to the batch. So they have to update simultaneously in order for synchronous to work. So that's why worker 1, after it's done, it cannot update it into the server. It have to wait until worker 2 to catch up with it and then update it. And it's very waste of resources. Let's talk about one strategy used in synchronous parallel data. Let's talk about one strategy using. Let's talk about free-scale synchronous parallel strategies, because as you know, as let's talk about free-scale synchronous parallel strategies. So usually, the fastest worker have to wait for the slowest worker. It's very waste of resources. Usually, it will check the whole system down because of the slowest node. So one strategy is used. So like each time a worker work inefficient, so we gave them a ticket. So for a certain amount of ticket, you will be excluded and punished, eliminated from the computation. So because the batch will still need the that parameter to be updated. So the neighbor of the slowest worker will take responsibility of updating the parameter of that worker. That's why we will divide the task equally to the remaining workers. After one go, we will divide the task like this. So for example, if P2 is get rid of, so right now this one is still updating P2. If P3 is gone, this one is continuing to update it. So if the whole thing is gone, there will be this and this. The next neighbor continue to update. So we will not worry about not updating parameters. The question is, so right now you already see a synchronous version and asynchronous version. So right now you already two versions, synchronous and asynchronous. So with those two methods, the question is, Is data parallelism enough to solve the problem? The answer is hard to say. Even though the synchronous update and asynchronous update, they're both fast. However, they still have problems that they need to be solved. For synchronous update, the communication and the synchronization costs increase as the model grows bigger. Slower node usually can track down the whole system because the faster node have to wait for the slower. For a synchronous update, usually sometimes the converge rate can be slower than the serial version, and a synchronous update is greatly dependent on the effectiveness of the model or the algorithm rate. So, in other words, both methods it have to be improved in order to work in real life because both still have some limitations that need to be fixed. So what next? Let's recap. To train a good model of machine learning, you require a lot of data because the more data you have, the better the prediction you will have. And it takes a long time to compute, like several days to compute one model. Why not choose standard method of data parallelism? The most common right now is asynchronous version and asynchronous version. Right now, many researchers are working on ways to fix the problem of each method. So which means we will have more new frameworks, new algorithms, and new models. Right now, let's just say that both versions are still on currently updated. So until then, we will still have to wait for a good model to be computed short amount of time. So right now, let's see what the future will have to offer. That's also the end of my presentation. Thank you.